Heidi ho, students. How we all doing today? You guys miss me? You're sad that I'm not here today. You probably thought that, hey, Mr. Bessling's not here again. We missed him last week already. Must be a free period. We must not learn anything. No, that's not true. You're still getting your lesson, so you should have your notes out. Good, you already have them out. Okay, let's get on with this lesson. We're essentially going to finish section 6.1 in the textbook, so I'm calling this lesson 2. As I mentioned yesterday, there was some theory I brushed to the side, and I'm still not going to hit terribly hard, but I still definitely want to go over, number one, a few problems. Number two, we're going to look at the requirements to use these confidence intervals for a mean. And number three, we're going to talk about the idea of a confidence interval, confidence level, like what do I mean by 99% confident? What do I mean by 95% confident? And we'll explore some relationships. And then we will finish this off with determining a minimum sample size to achieve some margin of error. Like I want to be able to estimate the height of JSerra students within a margin of error of plus or minus 1 inch. We'll get there, don't worry. Okay, so let's just kind of do maybe a problem here before we get going here. It's kind of like after our warm-up, but let's say we're given a confidence interval, 31.1 to 34.7, whatever the units are. What is the x bar, the average, and what is the sample mean, and what is the margin of error given this confidence level? Let's see if you can figure out how to do that. So there's I know you're thinking about it. There's always some symmetry involved here. Since we're essentially taking our mean and we're adding and subtracting our margin of error. So what's going to end up happening is wherever our mean is, it's going to be essentially halfway in between this interval. So how do I find the halfway point or the midpoint? Yeah, you learn in algebra something called the midpoint formula, which, even in statistics, guess what? It's just the average of these two. So I can add these together and divide it by 2. And now that is going to give me the mean. And hopefully you're putting this on your calculator like I am right now. And I got the midpoint there, which has to be my mean, at 32.89. So what about the margin of error? Well, the idea is since we're adding and subtracting the margin of error, this margin of error gets added essentially, how do I explain this? Sorry. Essentially, this whole length of the interval, which is going to be 34.47 minus 31.1, 31.31. The length of this interval, we're going to just cut it in half since the margin of error is essentially in there 2 times, right? Here's my, here. For instance, maybe here's my x bar, and this distance here is my margin of error, but I'm going to do that twice. So this whole interval ends up getting 2 margin of errors. So again, I subtract the end point from the initial point, so 34.47 minus 31.31, that gives me 3.16, and then I divide that in half. So this is my margin of error now. So I can even rewrite this confidence interval in this way. It's going to be the mean 32.89 plus or minus 1.58. So this is our first type of confidence interval that we have learned in this class. And I'm giving this a name right now. This is what we're going to call a z interval for mu. It's a z-interval, essentially because we use the z-statistic, a normal statistic, a normal distribution. And it's for mu because we're trying to estimate the population parameter mu, that is the true overall average or mean value from the whole population. Now the requirements to use this, we can't just really use this in any situation, and we haven't really talked about this. But how do I know if I create a confidence interval, if it's valid or not? Because I guess there's nothing that's going to stop me from doing the math, but how do I actually know that it's valid? Well, we can use this z-interval for mu, and again, when I say that, that's essentially, use this formula here. If, number one, and I did mention this before, our sample has to be random. We have to have a random sample. Again, if my sample's not random, my results are meaningless. And again, this is just one of the big problems with people misusing statistics. If they're not using random samples, there's essentially nothing that we can draw from. There's no conclusions we can draw from their sample because they're not random. They don't represent the population at large. Even random samples are not perfect, but that's okay. That the math can handle randomness. Number two, and this is going to go with the idea of a confidence interval, that what we've been using this what we're also calling the standard error, the sigma over rad n. You saw that before in last chapter, and that essentially came from the standard deviation, if you recall, of the sampling distribution. Hang on, this isn't a requirement, excuse me. But this, I'll change colors here. This number here came from the sampling distribution, the standard deviation of the sampling distribution. And we said that this was normal, and that's going to allow us to use this critical value of z under two conditions. And I know you remember what those two conditions are because you just took a test on it, right? What were those two conditions that we know that the sampling distribution of x bar is normal? Good. It's number one, it's either the sample size is over 30. I'll just write that in words. Sample size is 30 or more. And that was, that's an n, that was the central limit theorem. Or the population follows a normal distribution. And so far we haven't discussed this because, as I said, I wanted to just get us going on these. But this is very, very important about the idea of a confidence interval. So I'm going to just go back to that example that we were working on yesterday with just the JSerra students, the average height of JSerra students. So we're trying to estimate the true average height of JSerra students. Again, we can't sample everybody, so if we take a random sample, and again, I know we already did this, but let's again suppose we took a random sample of, and let's suppose that random sample had a mean of 68.32. Now, we get to assume that the standard deviation is 4 from the population. And let me just go back just real quick. This isn't in your book. The book only has 2 requirements of the z-interval, but I just wanted to put in this third, and this is what we already started with. Sigma, which again is the population standard deviation. The population standard deviation is known. And in reality, this is kind of a rare case. Why do I know the standard deviation of the population but not the actual mean of this population? Because that's what I'm trying to estimate, right? How do I know the standard deviation but not the mean? It's not impossible, but we'll start seeing, we'll have a better idea of that for the next section, 6.2, when we don't know the standard deviation of the population, which is more often the case. So going back to this, and let's suppose that we are going to sample 16 people. Our sample came from 16 people, and let's say we're going to do this at a 95% confidence level. So again, we're going to construct a confidence interval for the true average height. Now, here's the theory behind this. Since in this case, what we learned last chapter is since the population, and again, actually, let's put that in right now, that the population follows a normal distribution. That is, the heights of JSerra students, perfectly reasonable to assume that it follows a normal distribution, but we need to be told to do that. So, so here we go. So this is essentially what we just learned last chapter. We know the population follows the normal distribution, so we just kind of met, you know, the requirement that the sample size is 30 or more, or the population follows the normal distribution. We also assume that this was a random sample, and as we mentioned in this case, we know the standard deviation of the population. Okay, so the idea now is, if we kind of here's what we're going to do. We're going to, since we don't know the true mean of the population, we are going to assume, because it's an unbiased estimator, that the real mean of the population is our sample mean, 68.32. And this is a perfectly valid assumption to make because, as we'd mentioned yesterday, the sample mean is an unbiased estimator of the true mean. That is, even though we know this isn't going to be perfectly the mean, it doesn't tend to overestimate or underestimate the true actual population, the true average JSerra height, whatever it is, because we don't know what it is. So what we're going to do is, well, we know then if the real population has a mean of 68.32, then the idea is that the mean of the sampling distribution is also 68.32 inches. Now, what's the standard deviation of the sampling distribution? Well, that's going to be what we learned last time. The square root of, the population standard deviation, which was 4, divided by the square root of the sample size, which is 16. So that's 4 over 4, square root of 4 is 16, or 1. Okay, so why am I doing this? This is like last chapter, right? So here's what we're going to assume. We're going to assume the true mean is our sample mean, 68.32. But again, this idea of the sampling distribution having a standard deviation of 1 means that here's a standard deviation of 1, so this is 69.32 is 1 standard deviation, 70.32 is 2 standard deviations, and vice versa here. 67.32 is -1 standard deviations, and here's 66.32, -2 standard deviations. So again, what this bell curve with this standard deviation describes, if I were to take different samples, random samples of 16 people from this population and take the average of that sample of 16, this is the likely spread of those sample means. The idea is you're not going to see too many sample means, for instance, over 2 standard deviations or less than 2 standard deviations less than the mean. Most of the time, just about 95% of the time, it should be within 2 plus or minus 2 standard deviations. And this is going to be the idea of a confidence interval and the confidence level. So going back to this, just finishing this problem off, then our confidence interval, we can use this, again, we can use this formula because it met those requirements, and we could find our confidence interval that way. So our average was 68, our sample mean was 68.32. Hopefully you're going to start memorizing this number, 1.96. It's probably the most common critical value for at 95%. So that's the most common confidence level. So on the low side, if I subtract 1.96, sorry, I accidentally hit the plus button. So here's on the high side. I already did. Well, hang on. And if I subtract this, it's 66.36. So we're going to start saying when we're done with our confidence interval is that we're going to be saying that we're going to say here with 95% confidence we can say that the true, in this case again, what are we trying to estimate? We're trying to estimate the true mean height of JSerra students is between 66.36 inches, there's a decimal in there somewhere, and 70.28 inches. So I want to talk about what we mean with this, with 95% confidence or with 90% confidence. Does it mean that there's a 95% chance that we're right? Not exactly, not really. Kind of. We're either right about this interval or wrong. Like either the actual true average height is in that interval somewhere, or it's not. And I say that like that. Why? Because this isn't really a chance event. I don't know what the true average height of JSerra students is, but it exists somewhere. In theory, we could just pause time right now, get everybody's height, and we'd have it, right? It's almost like asking, hey, what's the probability that the Falcons just won the Super Bowl? It's something that already happened. It's, you could have asked me last week, what's the probability the Falcons will win the Super Bowl? And I could have given you an answer for that, or somebody could have tried to give them their best estimate for that. But after the fact that it's already been done, in this case, the probability is 0 because they lost in overtime. Okay, so I want to get back to this idea of what do we mean by 95% confidence or 90% confidence or 99% confidence. And this is a big thing in statistics. One way we kind of see, hey, what does this mean, is let's pretend like we actually knew the real average and standard deviation, and let's see what would have happened. So let's pretend that the actual mean, unknown to us, is actually 68 inches. And we'll leave that standard deviation at 4, and we'll still say it follows a normal distribution. So if the real mean was 68 inches, how did I do on my confidence interval? Great, right? Nailed it. And I say nailed it because 68 is in that interval. So here's what I'm going to do. I'm going to put a little number line up here. And this value right here in the middle is going to be the actual mean. And I'll put a few numbers on here, a little scale going up. And going down here as well. And I'm just going to draw a straight line down here, and this line is going to represent 68, which, as we said, was the true actual mean unbeknownst to us. So, for instance, this particular random sample of 16, got us a mean of 68.32. We didn't know at the time, but it ended up being pretty close. And our confidence interval went from about 66.4 to 70.28. 66.4 to about 70.28. So you can kind of think this right now, right there, that green line was my confidence interval, and in fact, if I stop that, not you, it's the stylist. I'm just trying to draw a dot, and then every time I don't know what it's doing. Sorry. So that's my mean right there, about. So that was, so the idea is that red dot was my sample mean, and the whole line represents the confidence interval. Well, okay, maybe that was my sample. Maybe you took a sample as well, and you had a different mean. Say it was like 67 over here, and you created your confidence interval. Sorry, there was the mean. I'm having trouble just making dots. It wants to do weird things. My app here, but maybe this was your confidence interval. So again, you were maybe a little bit farther off at around 67 as your sample mean, but still your margin of error in this case captured the true average. Maybe somebody else had a confidence interval where just by random chance had a couple extra tall people in their sample, maybe had an average of 69 point something, but still still in this case, 68 ended up being in their interval. And somebody else does this, and same thing. Maybe this one was like over here. Bam, nailed it. There's their 95% confidence interval. Okay, and then someone else, there's their interval. Someone else, and someone else. What? Huh? You missed it. And that just happened. Maybe that just happened by random chance. Maybe just randomly they got like 2 or 3 of our tallest basketball players, and just not very many short people to balance that out. And for whatever reason, maybe their average was like 71, their sample mean, and their confidence interval extended out to like 68.4 or something like that. So they ended up just being a little short, and that was just by random chance. Oh, darn. Okay, next person. Confidence interval, nailed it. Next one, nailed it. Next one, good. So here's the idea. At 95% confidence, the idea is if I were to take different random samples and different random samples of 16 different people and different people, the idea, what I mean by 95% confidence, is that 95% of these intervals will, as we say, 90% of confidence intervals will capture the true mean. Will capture, in this case, mu, the actual true mean. And that also means that, 5% of random samples by random chance got lucky or unlucky, depending how you're looking at it, just missed the mean. And this is the idea about 95%. So you can imagine if I did 90% confidence levels, about 90% of these intervals will capture the mean, and about 10% would miss. And if I dropped it down to 80% confidence, about 80%. So I'm just going to use the same scale, but maybe here in yellow I'm going to do 80% confidence levels. So maybe I did these same confidence intervals, and at 80%, do you think you'd get a longer or a wider confidence interval? Sorry, a wider or a narrower confidence interval. Yeah, you'd get a narrower confidence interval. And what's going to end up happening, like maybe this one right here, where we said, we had a big mean, since my confidence interval, confidence level that is smaller, my confidence intervals are going to be shorter, and only about 80% of these yellow ones we'll end up capturing the mean. This one definitely missed. So this is the idea about confidence levels. So I'll go back to that. All right, so a lot of times, for instance, it's desirable to choose to have a narrower window, right? We kind of, wow, if you look at that, just going back to our 90%, 95% confidence interval, 66 to 70, 66.36 to 70.28 is, as far as heights go, that's a decent spread. That's from 5'6" to 5'10". How accurate is that? Not super accurate, but we also have to respect the fact of a couple things, that we only sampled 16 people, and that the standard deviation of the population was 4, so there's a good amount of spread. I mean, if you think about this, we have people at this school who are 6'10", 6'11", and there's people in the school who are less than 5 foot. So because there's more of a spread, more variance, that also accounts for this kind of wide interval here. So a couple things here to achieve. So to achieve a narrower window, which is often a narrower interval, and I'm sorry my handwriting is not great on this stylus. Like it's just hard for me to write on here. There's two things I can do. For a narrower, I can decrease the confidence level, but then again, I could maybe miss the actual parameter I'm trying to measure. There's a better chance that I do that. Or what do you think the easiest thing I can do to get a narrow window is is take bigger samples, right? Increase sample size, if possible. Sometimes you just got to work with what you got, but clearly, the bigger sample size, the better it is. And again, I put an asterisk here. That's if it's random, right? If my sampling is biased, it doesn't matter how much I increase the sample size. In fact, I'll probably be even more biased. For instance, if I'm just sampling the basketball players, if I increase my sample size, I get a narrower window. I'm almost just like improving my chances that I'm 100% dead wrong about what I'm doing. So random sampling is always huge and important. Okay, let's talk about achieving. It's the last part of the lesson today. So we're almost halfway done. What, you think I'm joking? No, I'm not. I've lost my concentration. No, I was good. Achieving. Oh my gosh. It's my first day, guys. I'm just going to erase all this. Whoosh. Sorry. I should just pause, but I'm actually just trying to give you guys a little bit of time to digest this all, right? Processing time. You need processing time. Heavy lesson, right? We're not that bad. Okay, so we're going to talk about determining sample size. And the determining sample size, this is to achieve some desired margin of error. So, to achieve, that word is achieve, believe it or not, a desired margin of error. So, in other words, maybe how many people do I have to sample in JSERA to have a margin of error of plus or minus 1 inch, or plus or minus a half an inch, or plus or minus 1/10 of an inch? How many people do I have to sample? Well, luckily we know that the margin of error for our z intervals is this guy here again, the critical value of z times the standard deviation of the population. divided by the square root of n. So we're going to be, this is going to be our desired margin of error. This is going to depend on the confidence level, but we need to know what confidence level. And again, the sigma is supposed to be known. We're supposed to know the standard deviation of the population. So what we're going to be doing is we're going to be solving for n, which is our sample size. So I'm going to go to the next screen after you guys finish writing this down in just a moment. And we'll just come up with a nice little formula to solve for n, which is down there in the denominator inside the square root. So we're going to have to perform a little bit of algebra. Y'all ready for this? Okay. So my margin of error, we said, was this. So I want to solve for rad n. So step number one, actually, if I just multiply both sides by rad n, it's going to cancel out the left side. So I'll have rad n times e, our desired margin of error, equals z star over sigma. Now let's divide both sides by e. That'll get rid of it on the left side. And I'll have this. How do I get rid of that square root? Got to square both sides. So this is going to be the formula. So, and I'll say that n has to be at least, I'm actually going to turn it into a little bit of an inequality, because if I sample more people, right, this is going to, I should have a smaller margin of error. So let's use this. Let's try a problem. Let's do 2 of them. Then we'll call it a day after 18 more lessons. Haha, just kidding. So let's find the sample size. Again, this is just going back to the JSerra example. Find sample size needed for a margin of error. So the idea is to get a margin of error, to achieve a margin of error for either, let's do both of them, for 1 inch, and also part B for a 1/2 inch. Alright, so again, we're going to assume that the standard deviation of the population was 4, and we need a confidence level here, and let's just say for a confidence level of 95%. Alright, so our equation again was n has to be greater than or equal to z, the critical value of z times sigma over the margin of error squared. So to start out, and we're doing a 1 inch. So we have our critical value of z, 1.96 for 95%. I can't do decimals for some reason on my stylist here, sorry. And that's going to be times 4, which was the standard deviation of the population, divided by the margin of error that I'm desiring, which in this case is just 1. So this is going to be 1.96 times 4. Multiply them first, then square them later. And I got 61.46. So I have to sample 61.46 people, right? No, I always need to round these up. So I'm going to have to sample 62 people, at least 62 people. And that's going to have a margin of error of 1 inch, which actually means my whole confidence interval, since my margin of error is 1 inch, will be 2 inches long. Still a decently wide interval. So let's try part B. getting that confidence level, getting that margin of error down to a 1/2 inch. Did I go too fast? Here's that work. Sorry about that. No, I didn't go too fast. Okay, I went too slow. Okay, get on with it. Get on with it. All right. So part B, same thing here, but I'd like you to kind of see if you could tell what the relationship here is. Because if you notice, this margin of error is half the length as, a 1/2 inch is half the length of 1 inch, right? So again, we're using our confidence level, our critical value at 95%, which was 1.96. And that's going to be, now our new margin of error is 0.5. So this will be 1.96 times 4 divided by 0.5, quantity squared, and I get 245.86. But I can't sample 86 hundredths of a person, so I'll round this up to 246. Anybody see what the relationship was? First problem, we had about 62. To reduce the sample size, reduce the margin of error in half, how much did I actually have to increase my sample size by? Quite a lot, right? Yeah, it ends up being almost 4 times as much. Yeah, well, good news now. At least I know that that my confidence level, my confidence interval, is only going to be 1 inch off. 1 inch long. So I should have just about a 1 inch window of whatever the actual true JSARA height is, if I could manage to sample 246 people. And for the next part of the lesson, I'm going to end the lesson. It's a pretty good next part of the lesson, right? Any questions? Yeah, you in the back? All the way in the back row? Sorry, I can't hear you. Can you speak up a little bit? What? This is getting kind of awkward. Can you just maybe come visit me in office hours and then you can ask? Alright guys, I hope you like that bad joke, and I hope this lesson was useful, and I'll be back on Friday, and I will see you guys later. Thank you.